All right, welcome everybody. This is the third meeting of the Harvard Sports Analytics Lab and American Statistical Association section on statistics and sports seminar series for the fall. And I'm delighted to introduce to you our third speaker, who is Laurie Shaw. Dr. Laurie Shaw is a lecturer and research scientist in the Department of Statistics at Harvard University and a fellow of the Harvard Data Science Initiative. We don't have an institute yet. He holds a PhD in computational astrophysics and has previously worked in quantitative finance for the British government. His research currently focuses on sports analytics, applying statistical and machine learning techniques to extract information from data and creating tools to help professional teams make use of this information. So thanks a lot, Laurie, and please take it away.
Great. Can you just give me a thumbs up if you hear me okay? Excellent. So thanks very much, Mark, for the introduction, and to everyone for calling in to listen on a Friday afternoon. Before I get started, I'd like to acknowledge my collaborator, Sudarshan Gopaladesakan, who is the head of data science at SAL Benfica, which is an elite soccer team based in Lisbon, Portugal, along with the video analysts at Benfica who helped construct the training sets that we used in this work. Okay. So I think it's fair to say that there's been a kind of a bit of a data revolution in professional sport over the last few decades, and the game of soccer is no exception to that. If you go back to the mid-90s, the amount of data that was available to analyze, or at least to summarize, individual games was pretty much limited to some basic box scores. So essentially a count of the number of goals that either team scored, perhaps the number of shots they had, the number of yellow and red cards they received. So kind of roughly order 10 statistics per match. And then in the mid-90s, companies started to collect what in soccer is known as event data, and which is essentially equivalent in other sports to what's referred to as play-by-play data. And so event data is essentially a log of every on-ball action that takes place during a game. So each pass, tackle, shot, interception, where they occur on the field and when, the players that are involved, the outcome, as well as often some kind of secondary information, such as like whether the player used his or her left or right foot. And there are typically around sort of 2,000 to 3,000 events per match. So here is, this is what a goal looks like throughout an entire possession sequence in the event data. And big thank you to Metrica Sports and Toronto FC for sharing their data with us. So essentially in this image, every solid line with an arrow corresponds to a pass between two players. And then the dashed lines indicate sort of periods in which we infer that a player carried or dribbled with the ball. So in this possession sequence, the ball starts with the Toronto goalkeeper, Westberg, and there's a sequence of passes that end up with Nick DeLeon taking a shot and scoring a goal. And since around 2005, but really over the last decade or so, advances in machine learning and computer vision have enabled identification and tracking of individual players from video. So tracking data essentially provides a time series of the positions of each of the 22 players on the field and the ball at a frequency of 25 hertz. So 1 over 25 observations per second. And that produces about 150,000 observations of the player positions per match. So in this video, I've overlaid tracking data on top of the event data that I just showed in the previous slide. And you can see that it adds a huge amount of context, because now we can see what all the players were doing when they weren't in contact with the ball, which in soccer is the vast majority of the game. And so the completeness and the precision of this data is allowing analysts and researchers to break down matches into their smallest components, individual player actions, and build models to quantify the value of these actions, as well as to quantify or assess the quality of their decision making as well. So the wealth of data available can also help us to understand how players work together as a team, each moving in anticipation of what might happen next. So where the ball will go, where their teammates are, and what their opponents are doing. And of course, part of this anticipation is guided by strategy, essentially choreographed sequences of motion that teams practice on the training grounds and try to execute during games. And so one of the seminal pieces of work in this area is a paper published by Andrew Miller and Luke Bourne in 2017 called Possession Sketches, who looked at coordinated player motions in basketball. And in this work, they broke down player trajectories into segments. And so kind of examples of such segments are shown by the blue lines in each of these plots. And then they clustered these trajectories, representing each cluster as a Bezier curve, which is the blue dots and ellipses, which they referred to as action templates. And so to study coordinated player motion, they looked at the frequency with which pairwise combinations of these action templates co-occurred in the same possession, training a topic model to identify the distinct strategies used by NBA teams. And so kind of an example of the frequently co-occurring pairs of actions in a given strategy is shown in the right-hand side here. And so, in these cases, basically what you can see is that there's a player that runs directly towards the basket, whilst there's another player that's largely stationary in different parts of the court. And so essentially in this way, they were able to find a low dimensional representation of the different ways in which players coordinate and interact, and to analyze the different strategies used by different teams in possessions. Now, with 11 players in each team and a substantially larger playing area, soccer is extremely challenging to model in this way. However, there are certain situations in which the movement of players, particularly in the attacking team, so the team in possession of the ball, are highly synchronized to the point of being almost choreographed. And that's during set piece situations, in particular in corner kicks. So during corner kicks, players can have very specific instructions, so exactly where to stand and exactly where to run. And so what I'm going to do in this talk is focus on the methods that we've developed for identifying the distinct strategies that teams use in corner kick situations, defined by the coordinated motions of players, both in attack and defense. Okay, so let's just start off with some kind of corner kick basics. So a corner is awarded when a defending player knocks the ball over his or her goal line. And so the goal line being the end of the field that contains the goal that player is defending. Or in the case of the goal mouth, when the ball goes over the crossbar. And then the opponents get to restart play by kicking the ball from the corner closest to where the ball went out. So one of the 2 points marked X here. And typically what the opposing team will do with their corner kick is either cross it directly into the goal mouth and try to create a goal scoring opportunity, or play a sort of a short corner, essentially to try to retain possession. And approximately 80% of corner kicks are crossed directly into the opponent's area, and 20% are taken short, although of course this varies from team to team and from league to league. And there are on average about 10 corners per match, so 5 per team. And that means that in each match, teams can expect to have about 5 situations in which they can execute routines that they have planned and rehearsed in training. Despite the opportunity to prepare, the rate at which corner kicks are directly converted into goals is very small. So this table here shows the percentage of corners that produced a goal in 5 different leagues over the course of a season. And you can see that, across these leagues, from the English Premier League, the German Bundesliga in Denmark, Portugal and Spain, the conversion rate was typically less than 2%, or 1 goal for every 50 corners. Having said that, though, some teams have gotten pretty good at them. For example, FC Midtjylland in the Danish Superliga are known to put a huge amount of emphasis on researching and practicing set pieces. And in recent seasons, they've achieved conversion rates in excess of 5%. So that's 2.5 times the league average, and equivalent to a goal every 20 corners, or a goal in every 4 games or so. So let's look at an example of the kind of tactics that can be used at corner kick situations. And so what I'm going to do is, as I'm going to show you.
Yep. I'm sorry, there was a quick question in the chat. Are the proportions of corners conditional on successful entry?
Proportions condition is sex. What do you specifically mean by?
Brian, do you want to ask the question?
Yeah, so 2 slides back, or maybe 3, you had said that 82% were crossed directly into the box, 18% played short. Is this conditional on the corner successfully being played in, or have you already excluded the ones that are out?
You mean knocked out of play?
Yes, so maybe they kick it too far past the opposite sideline, perhaps.
Right. Okay, yeah, I mean, that's really rare. This is defined on, so I guess I measured this based on where the first ball interaction occurred. So if it didn't occur within the penalty area, then the corners that were kicked straight out of play would be ignored. But it's pretty rare. It doesn't happen, that often. Okay, so I'm not checking the chats, so just shout if you have a question.
Or better yet, put it in the chat and I'll shout.
Yeah, or Mark can shout at me as well. So we're going to show you an example of a corner kick situation. And so what I'm going to do is show you a video in which I've inlaid a movie that I created from the tracking data, which kind of creates a sort of bird's eye view of the action. And so let's consider the attacking team first. So it's the team in red is Toronto SC. And they have a corner kick, and the ball will come from the lower left corner, which is just off screen at the moment. And so what they've done is they've positioned 4 players in a kind of group towards the edge of the penalty area, this box here, which you can see I've marked here in the video and here in the overhead view. And they've also placed 2 players in the 6-yard box, sort of very close to the goalkeeper, almost interfering with the goalkeeper, which I marked here and here. So let's get this movie going, and what I'll do is I'll add tracks to the positions so that you can see of the attacking players, so you can see their trajectories as the ball is crossed into the box. So what you can see is that the cluster of 4 players that were at the edge of the area made sort of diverging runs into the different areas of the goal mouth. And one of the players that was initially stationed in the 6-yard box ran out towards where the ball came from, either as a decoy or to try to intercept the ball early. Oops. Okay. All right. So let's watch it again from the defensive side, and I'll slow it down this time. So the defending team have assigned 4 players to mark the 4 attacking players at the edge of the box, and they've also placed 3 players in what we refer to as zonal marking roles in the 6-yard box. So these 3 players here, and these players have been asked to defend essentially a high-value space or zone around the goal rather than marking a particular opponent. So if I get this going, there we are. And so what we see is that these 2 players here in zonal marking rows don't really make much attempt to follow this player as he runs out towards to potentially intercept the ball, whereas the 4 players that were individually man marking their opponents, largely their trajectories largely matched those of the players that they were marking. So you can kind of think of team strategies in corner kick situations as being drawn from a corner kick playbook, and the goal of this work is to read the playbooks and the tracking data. So on the offensive side, we want to identify the distinct corner routines that a team has used over the last 30, 40 games, defined by the runs each player makes, the coordinated runs that the players make, and the delivery location of the ball. And on the defensive side, we'd like to know which players have been assigned man marking roles, which have been told to zonally mark, and where those zones are located. And ultimately, the big question is, can all this information be exploited to defeat the defensive system and make corner kicks more effective? Okay, so just some information on the data used. We used data from a single season of an elite professional league, identifying 1,723 corner kicks from 234 matches, having removed the short corners, which aren't yet included in our analysis. And then for each corner, we extract the player trajectories from 2 seconds before the kick is taken to 1 second after the first ball interaction following the corner, which is a window of about 4 to 5 seconds. And we refer to the positions of the players 2 seconds before the kick is taken as being their initial positions, and their positions 1 second after the first ball interaction as being their target positions. And we use, just to kind of explain why we use 1 second after the first ball interaction, often what you see in these corner kick situations is that an attacking player doesn't necessarily try to get a shot at goal. They maybe try to divert the ball into a path of another player. And so we allow the sequence to run on a little bit after the first ball interaction so that we can get an estimate of, a better estimate of the target positions of all players. Finally, we also reflect the player positions so that the corner always appears to be taken from the left-hand side of the field. And so in all the examples you see from now on, corners are always taken from the left side. So to write all this out just a little bit more formally, the position of player I in team T, where team T can either be the attacking team or the defending team during a particular corner C at time T, is denoted by X, where the time variable ranges from 2 seconds before the corner is taken to 1 second after a player touches the ball for the first time after the corner is taken. And so this value here, T sub touch, is is obviously dependent on can vary from corner to corner based on where the trajectory of the ball. And so let's go straight on to measuring the offensive playbook. And so the objective here is essentially to construct a system for describing and classifying the set of synchronized runs made by the attacking players. And we do this in 2 steps. First, we classify runs by allocating each player to a pair of data-defined zones based on their initial and target positions. And I'll step you through that process in a second. And then secondly, we use non-negative matrix factorization to find a representation of the data that accounts for frequently co-occurring run combinations. Basically, the fact that the runs don't sort of occur independent of each other. There's obviously a predefined strategy and some correlation between the types of runs that players make. So our method for classifying attacking player runs starts by thinking about where they end up, their so-called target positions. So this here is a plot of the location of all the attacking players in our entire sample of corners. So it's about 15,000 players measured at their target position. So their position 1 second after the first ball interaction following the corner. And there are essentially kind of 4 features to this distribution of points. There's a large cluster in and around the 6-yard box, which reflects where the ball is typically delivered when it's crossed into the penalty area. There's a large cluster in this top left-hand corner, which corresponds to the position of the player that took the corner, a few seconds after they took the kick. There's a cluster of players outside of the penalty area, and these players are sort of typically waiting for to intercept the ball should the defending team manage to clear it. And then there's kind of a distribution of players here that were essentially anticipating a short corner, even though we've actually removed all the short corners from our sample. So these players could potentially be in a decoy. And so we fit a 15-component Gaussian mixture model to these target positions to identify distinct target zones. And we find that 15 components, and by that I mean 15 bivariate normal distributions, are sufficient to describe the data, and adding more components does not significantly improve the log likelihood of the fit. And so here, these ellipses represent essentially the 1 sigma regions for each of these 15 components. And of these 15 zones, we are only really interested in the 7 zones located within the penalty area, which I'm going to refer to as the active target zones. And so any player that ends in or near one of these 7 zones is going to be is included in our analysis and is referred to as an active player. And all the other players are now eliminated or excluded. So let's look at the initial positions of the players exactly 2 seconds before the kick is taken. And we're interested in particularly in the players that are going to reach or finish in one of these 7 target zones. And I've highlighted those players in blue on this side. So you can see that these form 2 clusters. One in the 6-yard box and one near the penalty spot. And it's also interesting to see that there's kind of 2 clusters up in the top left-hand corner, essentially one for a player that's about to hit the ball with his or her right foot, and the other with the player that's about to hit the ball with his or her left foot. And so to these positions, we fit a 6-component Gaussian, sorry, we fit to the points colored blue, so to the players that will end in an active target zone, we fit a 6-component Gaussian mixture model. And we'll call these the initial zones, and I've labeled them 1 to 6. So a player run is defined as starting in a particular initial zone and ending in a particular target zone. And with 6 initial zones and 7 final zones, that means there are 42 possible run types. So for example, here is all the runs in our data that start in initial zone 4, marked by the blue ellipse, and end in target zone C. So this would be labeled as run 4C. And I should say that I'm not marking the full trajectory of the players. These lines just join the initial positions and the target positions together. And here's an example of the run that we describe as 1A. So starting in initial zone 1 and finishing in target zone A. So all the runs made in a single corner kick can then be represented by a 42-element vector, where essentially each element corresponds to a unique run. So that's a combination of initial and target zones, with its value being the number of players that made that run in this particular corner. So with only sort of between 5 and 8 players actively involved in a corner routine, most of these elements are going to be 0. Now, our method for encoding corners is a little bit more complicated than that. So rather than assigning each attacking player to a single run type, we calculate the probability that they made each of the 42 run types by multiplying the probability that they started in the corresponding initial zone, sort of highlighted in blue here, and ended in the corresponding target zone, indicated in red here, where the probabilities are the Gaussian mixture model weights for that player. And so each element is a sum, essentially a sum over all players of the probability or the product of these probabilities. So as I've previously emphasized, the runs made by the attacking players are coordinated and synchronized. We expect to find sort of certain types or combinations of runs to occur together in our sample. And so we essentially draw inspiration from topic modeling to try to find a kind of a basis set of run combinations using non-negative matrix factorization to try and make some of this structure or some of these correlations between the run types explicit in our methodology. So just to kind of give a bit of background to non-negative matrix factorization, it's a linear algebra method that essentially decomposes a high-dimensional non-negative matrix, sometimes referred to as the term matrix, into 2 lower-rank factor matrices, sometimes referred to as W, or the features matrix, and H, or the coordinate matrix. So in our case, the term matrix has dimensions 42 by 1,723. So the rows correspond to each of the 42 run types, and each column is a corner kick, or the encoding of a corner kick in our data. The features matrix has dimensions 42 by n, where n is the number of unique features or the dimension of the new basis set, which you have to specify ahead of time. And I'll come back to how we do that shortly. And then the coordinate matrix has dimensions n by 1723, and it gives you the encoding of each corner in terms of the basis set given in W. So essentially, W defines the new reduced basis, and H gives the coordinates of each corner in that basis. And so there is, of course, some equivalence to principal component analysis, but whereas PCA does not in any way restrict the signs of the entries of the equivalent to the W and H matrix, non-negative matrix factorization requires all entries of both matrices to be non-negative, so that the data is described by using sort of essentially additive components only, as opposed to adding and subtraction. And for this reason, non-negative matrix factorization is often used in sort of image decomposition, basically trying to break down sets of images into sort of specific features. So we solve for W and H by minimizing a distance function. And in this case, the distance function is given by the Frobenius norm of the difference between X, the term matrix, and the product of the W and H matrices, plus some regularization on both W and H, where alpha is the regularization parameter, and it's typically set to something close to 1. And so the regularization helps to provide some sparseness to the basis set vectors, which is helpful because the number of attacking players that are actively involved in corners is typically between sort of 5 and 8. And so this helps kind of control that a little bit, or control the representation of corners. And so then the distance is minimized through a multiplicative update procedure where W and H are essentially iteratively and alternatively updated in a methodology that's not dissimilar to expectation maximization, and is described in these papers here. So one of the outstanding questions is how to choose the number of features or the dimensions of the basis set. And we do this by simply looking at how the Frobenius norm decreases as the size of the basis set is increased. So in this case, we selected essentially 30 features, or n equals 30, simply based on where this curve begins to flatten out. So this process is kind of a bit similar to picking clusters in sort of clustering algorithms like k-means using elbow plots. And one of the next pieces of, or at least one of the developments of this work, is to try and find better motivated ways of selecting this. So we've only essentially reduced the dimensions of the data from 42 to 30, but more importantly, what we set out to do was find a representation that acknowledges that some run types frequently occur together. So here's a kind of graphical representation of the feature space, or the basis set, basically plotting the sort of the run combinations that typically co-occur. And now we can essentially represent each corner in our sample as a weighted combination of 2 to 3 of these features. And you'll see that sometimes these features occur, correspond to 4 runs co-occurring, as shown in this feature down at the end. And sometimes it's just a single player, and that's because this kind of run, which is essentially a player just hanging around near the goalkeeper, the opponent's goalkeeper, occurs in many different corner strategies, and so that's why it's just corresponds to a single player. So here's an example of a corner in our sample. It only shows the attacking players. So the dot is their initial position, and then the dashed line is their trajectory, their full trajectory now. As the corner is crossed into the box, the black dots indicate the trajectory of the corner. And essentially, this corner can be represented by a combination of features 12, 18, and 25. So now we have quite a nice compact way of reconstructing the corners in our sample. So one thing we can do very easily now is search for our data set for corners that strongly exhibit a particular feature. So for example, if we look for the 10 corners that most strongly exhibit feature 12, we get this set here. And you can see that they all kind of have a number of things in common. Lots of players in a big group right in the goal mouth, and a player typically making this kind of run from what would be called the near post round towards the far post. So now, remembering that the H matrix encodes the corners in the new parameter space, we can cluster the columns of this matrix to find distinct corner routines. And so we essentially do this using agglomeratory of hierarchical clustering. So essentially look for corners that exhibit very similar features. And so this finally allows us to construct a playbook of corner routines for each team in our sample. And so, the query here might be find the distinct corner routines used by Team X over the last 20 games. And this would be the result. So what I'm showing here is the 4 distinct corner routines that we find in this sample of 20 games. The sort of the larger images show a kind of a characteristic example of each routine, and then the smaller images show basically other examples of each routine. And you can see that each of these corners all have kind of very distinct features. So for example, in routine 1, there's a group of players that start in or around the penalty spot. And there's typically a player that will make a run in and around, in behind the other players that he's initially located nearby to. Whereas in routine 2, one of the characteristic features is a player that starts at the near post and makes a run out towards the ball as they're crossed in. Routine 3 is a kind of an unusual routine in which players will line up on the far edge of the 6-yard box and make horizontal runs. And we can also demonstrate that the target location of the ball is also quite distinct from one routine to another. So now I'm plotting each X indicates the position at which the first ball interaction occurred after the corner kick was taken in each type of routine. And so you can see that in routine 1, the ball is normally expected to be delivered kind of quite deep into the penalty area towards this corner of the 6-yard box. And in routine 2, it's often delivered kind of close or beyond the near post, sort of around this edge of the 6-yard box. And so essentially, this enables teams to, once you can identify what the routine is, you should be able to have a fairly good example idea of where the ball will be delivered. Okay, so what I'm going to do now is move on to our analysis of defensive systems. I'll pause here for a second if anyone has any questions.
I'll ask a really super quick question. So since I know we've had a discussion before about how the non-negative matrix factorization is not unique, and you have this regularization that involves squared norms, I was wondering if there's a reason to have, say, the W matrix be more sparse, and so in which case you might actually have an L1 norm as part of the like I guess I was thinking, like, if you wanted to kind of restrict the number of the different pairs of target locations and initialization locations as your new coordinate system. I guess I was wondering if there's some advantage to taking the approach of making W sparse.
Yeah, I mean, so you can kind of play with the balance between L1 and L2 regularization in a kind of an elastic net type of way. The advantage of the L2 regularization, at least, is that it sort of by making the W matrix more sparse, it prevents you having sort of multiple, often more than 8 run types active. And because it gets quite hard to interpret when you have lots of different run types that are active, because it gets harder to represent corners in which there are only 5 or 6 attacking players. So there's a kind of almost an ideal level of sparseness where you want to pick up, key run combinations, but you don't want to have a dynamic basis set that's not sufficiently sparse that you can kind of it represents too many players at once. And so a lot of this was trying to find a balance between those two things. And I don't know if there's other than by judgment, I'm not sure there's kind of another way of balancing those two. And in the end, the clearer results, or at least when you follow the process right through to clustering and finding distinct corner routines, L2 regularization performed the best.
Okay. All right.
Okay, so defensive systems. So these images show the trajectories of the players in 2 different corner kicks. So the red team is attacking and the blue team is defending. And then the dots show the initial positions of the players and the lines show their trajectory as the ball is crossed into the box again. So if we just focus on the defending teams, the team in blue, and look at this, this left-hand image, we see what is a kind of a classic example of a zonal marking system. So the initial positions of the defenders, so the blue dots, are not correlated at all with the attacking team. There's no relationship between where the blue dots are positioned, where the red dots are positioned. And the same with the trajectories. You don't see any evidence that a defender is trying to follow a forward. On the right-hand side, we see an example of what is known as a hybrid defensive system, which is essentially a mixture of man-to-man and zonal marking defenders. There are clearly defenders that are marking man-to-man. Their positions are close to the initial positions of the attacking players, and the trajectories are obviously highly correlated with those of the attacking players. But there are also two zonal defenders, this player here and this player here, that aren't located near to an attacking player beginning the corner and don't really move much throughout the corner kick sequence. And so in most leagues, the majority of teams use some form of hybrid system. So the goal of this work was then to identify the role of each defender using tracking data alone. So how do we do this? So the first step was to essentially to agree with Benfica's analysts a set of predictive variables for identify man-to-man marking players. And I'll come back to what those predictive variables are in a few slides. So Benfica also provided a training sample of 500 corners, manually identifying each defender's role by watching videos of these corners, and essentially sort of manually and essentially by visual inspection identifying what their role was. And in this way, they tagged just under 4,000 defenders, 55% of which have been tagged as marking man-to-man, 45% tagged as zonal. So the kind of the data sample is quite well balanced. We then use the XGBoost implementation of gradient boosted decision trees as a classification model. So gradient boosting decision trees is essentially a method for combining an ensemble of weak learners, which in this case is individual decision trees, into a single strong learner in an iterative fashion. So XGBoost essentially grows them one at a time, seeking to reduce the residual errors produced by the preceding ensemble of trees. So the algorithm continues to build these trees, essentially making more and more combinations of splits until it reaches a predefined stopping criterion, either a maximum number of trees or a failure to find any further improvement of the model. And by using tenfold cross-validation across the training set, we achieved a classification accuracy of about 83%. And so essentially 5 in every 6 players were correctly classified in this way. Now, there are several different variables that are important in predicting role classifications, but I'm going to demonstrate how even just the initial positions are a useful discriminator. So the left plot shows the initial positions of defenders that were tagged as zonally marking in our training sample, and the right-hand image shows the players that were tagged as marking man-to-man. And there's very clear difference in the spatial distribution. So the zonal players tend to be kind of encircled around the goal mouth, whereas the man-to-man marking defenders tended to be in 2 clusters, either in the goal mouth or around the penalty spot. And if you remember, the image that I showed earlier in the talk of the initial positions of the opponents, it's pretty clear that the man-marking players, the distribution of their initial positions, matches pretty closely that of the attacking players. And indeed, if you just use a logistic regression on the initial positions of the players, you can get up to a 70% accuracy in terms of identifying the players of each type. The distance moved by a defender over the duration of the corner is also an important discriminator. So this plot here shows a histogram of the distance traveled by each defender in the training set, split by those that were tagged as marking man-to-man and those that were flagged as tagging zonally. And so you can see that the distribution of the zonal marking defenders of their distance moved is much tighter and much smaller, in the range of about 0 to 6 meters. Whereas the distribution of the man-marking defenders is much broader. Most of the defenders are in the range of 0 to about 16. So clearly this is also another discriminator. And if you add distance travel to the logistic regression approach, you get classification up to about 75%. The advantage of gradient boosted decision trees is they pick up a lot of linearity, and essentially that's what enables us using other variables to get up to a 83% classification. So one of the other discriminators that's quite important is the proximity to the goalkeeper. And that's simply because attacking teams often like to place the player very close to the goalkeeper to disrupt them. It's something that logistic regression has a lot of difficulty picking up on, but the decision or XGBoost is able to capture quite nicely. So the most predictive variables in the model in terms of based on importance on their F-score, which is essentially the metric that sums up how many times each feature is split on in the final ensemble, is the positions and the distance traveled by the defenders, the proximity to the goalkeeper, as I've mentioned, as well as variables that measure the distance traveled by nearby attacking players and by nearby teammates. And that sort of helps you pick up when two players start very close to each other. It helps you sort of pick up whether the one player is man marking or the other is, or they both are. So with our role classification algorithm, we can now automatically tag the roles of each defender. And so here are movies of the two corners that I showed a few slides earlier, now also indicating the role classifications of each defender. So the large circles indicate zonally marking defenders. The stars, and there aren't any in this case, indicate man marking defenders. Upside down triangle is the goalkeeper. Small circles are essentially other outfield players who aren't really directly involved in defending the corner. And the red circles are the attacking team. And so if I get this playing, you can see that the defending players, the big circles are clearly zonally marking and don't really correspond to the or correlate with the trajectories of the attacking players. Whereas in the hybrid system, now we have a number of man marking players that are correctly identified. These stars here located initially very close to attacking players, and as we'll see as we run this movie forward, these defenders track very closely their opponents. So I'll play that again. So one of the interesting things you can do now is that now that you can find the zonal players in the data, we can also study where their zones are located. So for example, Team Y consistently used a hybrid system throughout the 2017-18 season in our sample, with essentially using 4 zonal players and 4 man-to-man marking players. And so here I've plotted a heat map that shows the distribution of the positions of the zonal players measured over 30 matches. So it's around 200 or so corners. And the locations of the 4 zones are very clear. You can see them indicating sort of here, 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 and here. And it turns out that when you look at the identity of the players, they were pretty much always the same players. So player with jersey number 4, 28, 3, and 2. And actually, the player number 4 is the right back, and player number 28 is the left back, and 3 and 2 are the 2 centre backs. So this information can clearly be used to help analysts and coaches to identify the structure in the opponent's defensive system and try to find ways to exploit it. And so I'll finish with a kind of a small example of this, particularly by asking the question, where do different zonal systems concede shots? So what I'm going to do is compare the shots and goals conceded from corner kick situations by 2 different hybrid systems that we use frequently and by multiple different teams in a sample of 3,500 corners extracted from 2 seasons of tracking data. So essentially doubled the size of our data set. So here is a heat map of the first system. It includes 4 zonal defenders positioned in a ring around the goal mouth, and the X's indicate the most likely positions, so essentially the mode of each of these distributions. And this system was used by a defending team in about 366 corners in our sample, although multiple different teams used it. The second system, it has just 2 zonal markers. So the expected position of the markers is here and here. And note that also these zones are also kind of located closer to the goal than the zones in the 4-zone system. And so this 2-zone system was used in about 600 corners in our sample. And of course, there are man-to-man marking defenders in both systems that are not shown. So let's now just first plot the delivery location of the ball in each system. So the black points mark the position of the first ball interaction following the corner, which could be either by a defender or an attacking player. And so immediately you can see a fairly striking pattern. In the 4-zone system, corners were typically aimed further away from the goal than in the 2-goal system, in the 2-zone system. And you can see almost that there's a kind of hole in behind the ring of zonal defenders in which very few corners were delivered, whereas in the 2-zone system, there were quite a lot of corners delivered right into that area. And so if I kind of flick back and forth between the two, you can begin to see how the spatial distribution of these points is different in each case. So now let's look at which of those corners produced shots. So the blue circles indicate the corners that produced a shot on goal within 6 seconds of the corner being taken, and the stars indicate corners that actually produced a goal. So in the 4-zone system, most of the shots came from corners delivered outside of the 6-yard box. Whereas in the 2-zone system, about a third of the shots came from corners delivered within the 6-yard box, and almost 2/3 of the goals. And in fact, you can see that a lot of the goals were created from corners delivered almost essentially in between the 2 zonal markers or into the far post. So what have we concluded from this? Not necessarily that the 4-zone system is better. It actually appears to concede shots at a higher rate, so 33% to 27% than the 2-zone system. However, the quality of these chances conceded by the 4-zone system was significantly lower, so 7.5% as compared to 13% resulted in a goal being scored. And so this kind of information is the sort of information that teams that we work with are directly interested in. What is the effectiveness of different defensive systems and in different situations? Okay, so where next? The first step is to develop automated tools that can be used by the teams that we work with for opposition analysis, producing reports and interactive visualizations, syncing with video, highlighting useful information. We're already sort of almost trying to validate this methodology by providing some reports to the teams we work with and seeing how they correspond to the match that then happens. And the feedback we're getting from that is that they've turned out to be very useful. But the next sort of bigger question is to understand which attacking routines are the most effective against a certain defensive system. And so the goal here is clearly to try to understand, given a certain defensive system, what attacking routines are more likely to create a goal scoring opportunity. And to achieve this, we'll apply the tools that I presented today to a much larger sample of data collected across multiple leagues. And that helps reduce the chances of being confounded by other variables, such as just how good the team were or the quality of individual defenders. And this will enable us to empirically investigate the most effective chances for boosting the quantity and quality of chances created in corner kick situations. And that's it from me today. Thank you very much for listening.
Okay, thanks a lot, Laurie. So we'll open it up. If people have any comments or questions, best thing to do would be to raise your virtual hand. We just call on you.
I'll let you call on people, Mark.
Okay. You may not need to. Any thoughts, anybody? I'll ask a quick question. So I know you're at least for the offensive schemes, that you're basically focused on where players start and where they end. Is there any value to including some information about the trajectory of player movements? I know that expands the state space, but I'm wondering if that potentially adds some value.
Yeah, it would. So we typically, when we think of, we tended to think of players just sort of starting somewhere and trying to get to somewhere, but often, especially when you talk to people who, coaches, people involved in the game, there are other things that a player might try to achieve, such as, blocking and, picks and so on. And the full trajectory information will help to kind of understand that. And the idea there, you can sort of follow the methodology of the paper that I discussed right at the beginning, possession sketches, and try to kind of actually produce a full model, time series model of different trajectories and cluster those trajectories. Initial work that I've done on that demonstrates that most players do actually typically largely run in straight lines.
And you're looking at very small amounts of time anyway, compared to what they were doing in basketball anyway.
And also a much larger field. And, in basketball, I think because of the restricted playing area, I think players tend to need to stop and turn, more rapidly. But there is clearly information in there. It's the tricky thing is just trying to figure out an efficient way of extracting it. But it definitely is kind of on the list of things to do.
I'll ask one more in case if nobody else has any other questions. In the defensive setup, so you're basically learning, you're learning the labeling of zonal versus man-to-man from essentially information that's provided to you. And I assume when you're talking about applying this to other leagues, you're essentially going to take the model that's learned from this data and apply it to these other leagues. But is there do you have any concerns about how that model might, whether it really extrapolates to the other leagues, or is that you think that should just be a pretty straightforward longitudinal move?
No, there are concerns. I mean, one of the concerns is simply that you have a different data provider, and sometimes the quality of the data is not quite the same. So there is, I suspect that there would have to be some degree of retraining, or at least training about a creation of a small training sample, just to ensure the model performance doesn't vary enormously from one league to another. In terms of sort of like more inherent differences in the way that leagues play, and I'm not sure that there's anything else that necessarily would cause it to perform more poorly in other leagues. But it's something we haven't done yet, so I don't really know what the outcome of that will be.
Fair enough. Debangan, you have your hand raised.
Yeah. Hi, I'm Debangan. I'm a PhD student in biostats, so I was really interested in this talk, and I was interested in the first part where you defined the dictionary of player runs for the attacking players in the corners. So I was wondering, like, is there any specific type of, like, from that dictionary, like 1A, 2B, 3C, sort of that? So is there any type of specific runs like that would help in a specific defense, like that would help against a specific defensive marking system, like zonal or hybrid, like just contrasting one against another? Is there any result about that?
I mean, it's something that I've avoided doing just because of the risk of being confounded. So for example, in the data set that we have is two seasons from a specific league, and there are only one or two teams that use a predominantly zonal defensive system. So you would almost be asking the question, how effective is that run against that team? Part of what the answer you may get would be because the effectiveness against a zonal system, part of it might just be how good is that team actually defending. And so for that reason, trying to identify distinct routines and try and figure out how well they do against specific defensive systems is something that requires a much larger sample of to kind of try and dilute away some of that confounding effect. So I mean, I guess the short answer is we haven't looked at it yet, but purposely because it's because of that concern.
Yeah, thank you.
Nate, did you have a question?
Yeah. So I was just curious about, I know that the talk was about the corners that are, played into the box. You don't really look at the short kicks that, maintain possession for the offensive team. But I was curious just about the relative frequencies of both those strategies. Like, and maybe I missed it, maybe you went over it, but like, is there a trend? Do more teams play the ball, high into the box, or, and I guess has that changed over time, or is it still playing a short ball just to maintain possession, like something teams frequently do?
So, so 80% of, or just over 80% of corners tend to be played directly into the box. So short corners are, rarer in comparison.
Okay.
I suspect that the frequency with which teams use short corners is team specific. Intuitively, some teams prefer to maintain possession and are less confident of creating goal scoring opportunities by just playing high balls into the box. The difficulty with analyzing those is that the players have moved around a lot more, and the idea of kind of correlated runs has kind of disappeared at that point because they moved basically into open play. Because we have right now we have 2 seasons worth of data for the same league, which isn't really enough for identifying whether there's a trend towards more teams using short corners or less. They do seem to be less effective.
Okay.
If you kind of broaden out the time span to like 10 or 20 seconds and look at the frequency at which goals are scored, you tend to find that short corners produce less goals. But of course, some teams are kind of well known for using them, and so maybe perhaps there's a reason for that.
Interesting. Thanks.
All right, we're at the end of the hour, so why don't we thank Laurie once more. So appreciate everybody coming to join us. We'll have another talk in 2 weeks, and we'll send out the announcement about that pretty soon. So have a great rest of your Friday and a great weekend, and we'll hope to see you all soon. So thank you very much.
Thank you very much for everyone for logging in and listening.